Let's jump right in. Welcome to Phase 3, where we're stepping into the shoes of a senior protection and quality engineer. Today, we're diving into Part 1 of Symmetrical Short Circuit Analysis, focusing specifically on AC and DC decrement. We're going to break down the split-second dynamics of fault currents and look at exactly why they matter so much for everything from breaker sizing to overall grid stability.
So here's the game plan for this explainer. First, the anatomy of a fault. Second, we'll deconstruct AC decrement. Third, we'll look at DC offset and the X/R ratio. Fourth, we'll tie that into substation grounding safety. And finally, number 5, we'll explore grid strength and renewables.
Let's kick things off with Section 1, the anatomy of a fault.
You know, the instant a three-phase fault hits, the current doesn't just cleanly jump to some new steady value. Nope, it spikes asymmetrically, it rides on top of this decaying DC offset before finally settling down into a smaller, symmetric waveform several cycles later. To really wrap our heads around this, we have to recognize that the actual fault current is mathematically broken into two completely distinct parts, a symmetrical alternating component and a unidirectional DC component. And depending on whether you're a breaker manufacturer, a relay engineer, or designing switchgear, you care about very different points on that resulting curve. It's fascinating to consider the layering effect going on here. If you were to strip away that exponentially decaying DC component, you'd be left with a perfectly symmetrical AC current. But in reality, when a fault actually occurs, those two components sum together, creating a massive, lopsided, asymmetrical peak. So a fault current isn't just one unpredictable, chaotic spike. It's actually two completely separate, highly predictable effects layered right on top of each other.
Which brings us nicely to Section 2, deconstructing that AC decrement.
Now, what's really fascinating is the behavior of just that symmetrical AC portion over time. The AC decrement follows a really smooth, three-stage decay based directly on the generator's reactances. We're talking incredibly high current during the subtransient period, governed by reactance X''D, for about the first 0.05 seconds. Then it drops into the transient period, governed by X''D, and eventually settles into a stable, steady state, governed by synchronous reactance XD. Honestly, if you're already familiar with generator reactances from Phase 2, there's absolutely nothing fundamentally new here. It's that exact same three-stage decay, just applied dynamically to a real-world fault.
All right, moving right along into Section 3, DC offset and the X/R ratio.
Think about this. When a fault occurs at a completely random point on the voltage wave, the current literally cannot jump instantly. Because of the system's inductance, it's forced to start at its exact pre-fault value. So a decaying DC exponential offset basically appears out of nowhere to make up the difference, keeping the math and the physics balanced. And here's the kicker. How fast that offset decays depends entirely on one single metric, the circuit's X/R ratio, meaning the ratio of system reactance to resistance.
Let's look at the extremes. Out on resistive distribution feeders, you've got a low X/R ratio. That DC offset decays rapidly, often dying out in literally just one cycle, and the fault current becomes symmetrical almost immediately. But get near large generators and transformers, and reactance heavily dominates resistance. That creates a high X/R ratio, meaning the DC offset decays super slowly, causing that lopsided, asymmetrical fault current to linger for many cycles. And guys, this is absolutely crucial for breaker selection. A breaker rated only for symmetrical current might literally blow up on a high X/R system. Why? Because the actual peak current it has to interrupt, including that lingering DC offset, is significantly higher than the RMS value alone.
So let's do a quick mental check. A fault near a large generating station shows current still highly asymmetric after 3 cycles, while fault way out on a distribution feeder looks symmetric almost immediately. Why? Well, as we just saw, it's all about that X/R ratio. The high X/R near the generator gives a painfully slow decay, which absolutely demands a breaker with a much higher asymmetry margin.
Let's shift gears a bit for Section 4, substation grounding safety. Because getting this math right isn't just about protecting expensive equipment. It's quite literally a matter of human life and death.
IEEE grounding standards strictly require engineers to use something called a decrement factor. This decrement factor is an adjustment used to convert that highly dangerous, transient asymmetrical wave into a workable, symmetrical RMS equivalent. It accounts for both the initial DC offset and exactly how it attenuates over the entire duration of the fault. But why does this actually matter on the ground? Well, applying this decrement factor directly dictates the maximum grid current sizing.
For faults lasting under a second, which is exactly where that DC offset is strongest, this calculation ensures the physical copper grounding grid buried beneath the substation can rapidly and safely dissipate the fault. If you size those conductors too small, they might melt, or far worse, they could generate lethal step and touch voltages right on the ground surface where personnel are walking around.
When we analyze safe body current limits, notice the distinct fibrillating versus non-fibrillating zones based on body weight and fault duration. There is a very clear threshold where an electric shock turns fatal. If our initial calculations for the X/R ratio and the DC offset are wrong, the ground grid could fail to dissipate the energy, and the resulting service voltage could drive a body current straight into that highly dangerous fibrillating zone. It really puts the math into perspective, doesn't it? Okay, moving to Section 5, Grid Strength and Renewables. Now, everything we've talked about so far assumes traditional, rotating, synchronous generators, but we have to acknowledge that modern grids are fundamentally shifting.
Let's compare how traditional, high-inertia synchronous machines behave during a fault versus inverter-based resources like solar and wind. Traditional synchronous generators interface with the grid through massive, rotating physical masses, inherently providing huge short-circuit current and a natural physical resistance to frequency drops. On the flip side, inverter-based renewables connect through power electronic converters. They provide almost zero natural inertia and severely limited short-circuit current, which entirely shifts how fault wave behaves.
Because these power electronic converters severely restrict fault current, having a high penetration of renewables ironically lowers the overall system strength. We get what protection engineers call weak grid conditions. Those massive, traditional asymmetric fault current spikes that we rely on to instantly trigger our protective relays, they might not even happen. This drastically increases the risk of cascading failures, severe voltage drops, and widespread frequency instability during grid disturbances.
So here's the big question. You now understand the intense, split-second physics of a single fault originating from a generator, and you see how renewables are shifting the landscape of grid strength. But how on earth do we model a short circuit across an entire region? If modern grids contain hundreds of interconnected buses, some fed by traditional synchronous machines and others by limited fault current renewables, how do you determine the exact asymmetrical peak at one specific substation?
Well, that is the exact mathematical challenge we are going to conquer in Part 2 of this explainer, when we dive into network fault calculations and Z-bus matrices. We're going to take the single source fault behavior we just learned, scale it way up, and calculate fault current across massive networks using one unified matrix. If inverter-based renewables are making our grids weaker and fault currents harder to predict, how will our traditional protection relays even know when to trip? We'll uncover exactly how to answer that when we collapse the entire grid into a single Thevenin equivalent circuit next time. You definitely won't want to miss it.